25 and 26, we learned how lenses affect our ability to see light. We also learned how refraction changes the apparent location of an object. We are now going to talk about diffraction and how it affects our vision, and how it can be used to understand the Retina display and other high-definition lenses and screens. The definition of resolution is the ability to separate closely spaced objects from one another. We will see that there is a difference between the scientific world's understanding of resolution and the technology's understanding of resolution. Diffraction refers to the bending of waves as they pass through a barrier or through an aperture, such as the human pupil.
Criterion states that the minimum angle that can be separated is equal to 1.22 times lambda over diameter, where lambda is the wavelength of light and the diameter is the diameter of the aperture which light travels through. In the case of the human eye, the human pupil has... I messed up already.
No, just keep going. Keep going.
All right. In the case of the human eye, the aperture is the human pupil. And the human pupil has a diameter of 5.00 times 10 to the negative third meters, which gives a minimum angle of 0.00770 degrees, which is very resolute.
Yes, good. No. Apple defines the Retina display as any display in which the individual pixels cannot be separated by human vision. Traditionally, this occurs when the pixel density surpasses 300 pixels per inch, which is accepted as a threshold for human vision. However, since resolution is a function of distance between the viewer and the viewed object, Apple has made displays such as the new iPad, which have less than 300 pixels per inch, and yet are still Retina displays. This is because 300 pixels per inch is the threshold of the human vision. 300 ppi is the equivalent of 1/60th of a degree, or 1 arc minute. This is a threshold for human vision. However, there are some Retina displays that are so qualified despite having less than 300 pixels per inch. The reason that they can be qualified as Retina displays has to do with the viewing distance. The greater the viewing distance, the less pixels per inch is needed to be qualified as a Retina display. This is because resolution is a function of distance from the viewer and the object being viewed. Resolution is a function of the aperture size that light travels through, which in our case is the pupil. At night, a person looking directly at the light of a clock sees a blurred image of time. But when the person looks into the darkness and indirectly sees the light, you can observe a clearer and more resolute image of the time. This is because when your eye looks into darkness, it is able to see things with more resolution. But when your eye looks at the light in the clock directly, it is not able to see with as much resolution. The distance at which a person is able to distinguish two different light sources of light is a function of how far apart the two light sources are. The classic physics problem is a car with two headlights approaching a person in the middle of the road. At a distance, the two headlights appear as one, but as the car approaches, the viewer is able to distinguish the two light sources. The idea behind the Retina display is to completely eliminate the distance at which a person can distinguish between two pixels, essentially by making them invisible. In this case, the goal is to create an image that appears complete without any awareness of the individual pixels. This requires a higher pixel density in consideration of the proper viewing distance of the object.
In order to find how small a pixel must be in order to be essentially invisible, observe the following equation. Using SOHCAHTOA, we find that the tan of the viewing angle divided by 2 is equal to the pixel spacing divided by 2d, where d is equal to the distance where the pixel cannot be seen, making the display Retina.
Slide. As you can see in this chart, pixels per inch does not necessarily need to exceed 300 pixels per inch in order to be qualified as a Retina display, although higher pixel density certainly provides a clearer image. However, the realistic viewing distance also factors into Retina display. While both the iPad 3 and the MacBook Pro 17-inch computer have less than 300 pixels per inch, their viewing distances exceed that of the iPhone, which necessitates a higher pixel density in order to provide a Retina display.
This chart shows a wider variety of displays. The table compares the item's actual resolution versus the resolution needed to be considered as Retina display. The column labeled interpixel spacing represents the S in our equation tan of A over 2 is equal to S over 2D. Those items with the lowest value for S, the 17-inch MacBook Pro, the iPhone 4, the iPad 3, the Blu-ray, and the Asus tablet also have the highest resolution Retina display, verifying our equation. Notice that while the iPhone has pixels of 960 by 640, its screen is far more resolute than the iPad 2's 1024 by 768 pixels. This is because the PPI for the iPad is much lower. This slide demonstrates the human brain's capability to distinguish letters and words. The top lines show letters produced 1 pixel by 1 pixel. They are very difficult to process, however, the second line also contains letters 1 pixel by 1 pixel, but are arranged into a sentence. Despite the identical size of letters, the sentence is easier for the human brain to interpret, as that is a main function of the human brain to recognize patterns even in sight. This picture compares the resolutions of the iPad 2 and the new iPad. As you can tell, the same image viewed side by side on the regular display and the Retina display appears clearer on the Retina display. This is because of the viewing distance is around 12 inches. The human eye cannot separate the pixels, whereas on the iPad 2 display, the words appear fuzzy because of the lower pixel density. This shows a contradiction between science's and Apple's understanding of resolution. For technology, resolution says that pixels cannot be separated, whereas scientifically, resolution refers to the separation of pixels.
In regards to television resolution, the most popular resolution TV sold is the 1080p, a perceived advancement from the 720p version. However, comparing the functionality of the two versions, tests have shown the two to be extremely similar. Other than the $250 price jump to move from 720p to 1080p. For starters, cable and national TV broadcast using 720p cameras, not even 1080p cameras. Only certain on-demand stations even broadcast in 1080p. And since resolution is a function of distance, we will consider the average viewing distance at 8 feet, or 72 inches. At this distance, experiments have shown that for TVs under 50 inches, a distinction between the 720p and 1080p screens can hardly be made. Therefore, when considering paying the extra $250 to upgrade to 1080p, consider screen size. One advantage of 1080p is for those who use games set in 1080p, which are becoming more widely circulated, or for those planning to make heavy use of a Blu-ray player or projector. For these two situations, the full extent of 1080p displays are utilized, as both are specifically created for 1080p screens. But for all those who just enjoy watching a movie from time to time on a modest, less than 50-inch screen, you're safe to stick with the 720p screen for now.